Okay, so continuing on the kind of optimizations that can be performed in order to get better performance from your circuit. Apart from pipelining, the next thing that can be considered, and again I'll be talking about this only at a fairly high level, right, is parallel execution. Now, in order to understand what we mean by parallel execution, the simplest way to think about it is when we think of a CPU, right, we have instructions being executed by the CPU, and the best way to look at it is there is a single ALU in there, an arithmetic and logic unit, that can perform operations one after the other. So, if I wanted to, for example, multiply or perform a dot product, right. So, I have A1 B1 plus A2 B2 plus A3 B3. There are 3 multiplications to be performed over there, but the CPU will first have to do A1 into B1, then A2 into B2, and then maybe add the result to what was there before, and then A3 into B3 and again add the result into what was there before, right. Now, that is essentially a sequential mode of operation. But if I know that I am repeatedly going to be performing dot products, perhaps I can create some kind of custom hardware that is capable of performing A1 into B1, A2 into B2, A3 into B3 all at the same time, right. It would require more hardware, but it is good if I have regular operations. What I mean by regular operations is if I know that dot products or matrix multiplication are something that I am going to be performing very often, then it makes sense for me to create extra hardware, right, which performs a lot of multiplications all in parallel at the same time, so that my overall execution, my speed of operation can be more. Now, if you think about it, right, it is not as simple as that, because I need to perform A1 into B1 and I need to perform A2 into B2 and A3 into B3 all at the same time, but which means that I need to be able to read all those values A1, B1, A2, B2, A3, B3 also into my computational units at the same time, which means that I need to have some way of getting a large amount of data into my computational unit or my ALU in a single clock cycle. So, parallelism can be applied judiciously, can be used in order to sort of get better throughput, but only if we are careful about can we also provide the data to the system as required. Now, there are many types of parallelism that come up when we start looking into the actual implementation of digital hardware. The most sort of basic one, looking at it purely from the point of view of the digital hardware, would be what is called data level parallelism, right. And this, the example of the dot product that I gave, A1 B1, A2 B2, A3 B3, as long as I can get all that data into my system at one shot, I can perform those computations in parallel. Now, some of you may already have looked a little bit deeper into the kind of instructions that are there inside CPUs, and you may be aware of the fact that there are things called AVX and SSE, the advanced vector extensions and the streaming SIMDs extensions and so on, right, which ultimately are trying to do exactly that, right. You have a large amount of data that needs to be processed. Can I provide a very regular structured kind of hardware that allows me to perform all of those computations in parallel? This is called data level parallelism. Now, inside a CPU, it turns out that there is also something else that you can look at, which is called instruction level parallelism. Instruction level parallelism basically says, if I have, let's say, an add instruction, and immediately, or rather if I have an add instruction, after that I have a load instruction, and then maybe I have another branch instruction coming up after that. What if the add instruction is working with register R1, R2, whereas the load instruction was trying to load something into another register, let's say R7 or so? There is nothing fundamentally which says that the add must happen before the load. It may be possible to do the add and the load in parallel with each other, especially because the add uses the ALU, whereas the load actually needs to go and fetch data from memory. So, given that they are accessing different units of hardware or different parts of the system, why can't I think of running them at the same time? That has been exploited in the context of CPUs as well as DSPs, which are specialized kind of CPUs used for digital signal processing, right? And there was also a number of CPUs themselves, including something from Intel called the Itanium, which is no longer in practical production, but was an interesting architecture at the time. There is also this notion of what's called superscalar execution, which is there pretty much in most CPUs these days. Both of these are trying to essentially find out instruction level parallelism. Are there ways by which multiple instructions could be executed in parallel at the same time, and if so, can we go and run them, right? And of course you can take that one step further and say I can look for what's called task level parallelism, where I can actually think, for example, at the operating system, right? If you have looked into what happens inside an operating system or what's running inside your Windows or Linux or Mac OS based machine, you know, for example, that there's, let's say you are browsing, or maybe right now you are watching a video, right? At the same time there is audio playing which allows you to listen to this lecture. In the background there is some network activity that's happening in order to actually download the data. You might also be having a clock, for example, that's running and updating the time, and there would be some other periodic checks that are, let's say, going and checking whether you have new email or a WhatsApp message, right? Now obviously there are a whole bunch of different tasks that are running on your system, and effectively they have parallelism associated with them because there is a potential to be able to run more than one such operation at the same time, right? So as you can imagine, right, and as we already discussed in the previously when we were talking about systems on chip, increasingly the move is away from pure digital level, the hardware level execution, towards something that is programmable and in fact moving extensively towards software, right? At each of those levels there is some level of parallelism that you can observe and hopefully make use of, right, in order to improve the overall performance of your system. Now there are a number of optimization techniques, right, that can be applied in general across both hardware as well as software, and in order to understand this, actually speaking, the right thing to do would be not just purely focus on digital design. You need to understand a little bit more about how the synthesis tools and the compilers work, right? In the course on C, we already looked a little bit at how C compilation works. We basically said that, you know, there is a parser that takes the C code and converts it into some kind of intermediate representation, and then there are certain kinds of optimizations that can be run on that code, right? The same thing happens in hardware, because at the end of the day when you write Verilog code and you try to synthesize it, there is actually a compiler that takes that code and tries to generate a corresponding set of gates corresponding to that code. Now you could also have something where, let's say, you even write something like a hardware loop in Verilog, right, or in a language like C, and potentially you could have something where perhaps the compiler might take this loop and actually break it up into a sequence of, let's say, 8 different operations, right, because which happen one after the other. A normal C compiler would do precisely that. It would basically say, okay, I have to repeat this loop 8 times, and each time I need to do a multiplication followed by an addition and accumulate into this result. Now what if I had a piece of hardware or a CPU that had 2 multipliers and 2 adders built into it, right? I could actually write my code something like this, where I would basically say do A of I and B of I, A of I plus 1 and B of I plus 1, do both the multiplications, and now the sort of the way the compiler can look at it is, it can see this data and say, okay, I could actually do these 2 operations in parallel, right, because I have 2 multipliers in my hardware. I also need to, of course, figure out how to add them both in parallel. Maybe I'll add them into a temporary variable and then finally accumulate into the result. The interesting thing is, this for loop now runs only half the number of times as what it did in the previous case, which means that as long as the compiler is able to make use of this optimization, it could actually finish the work in half the time of what would have normally happened. Of course, it needs the hardware to be capable of supporting this, but if so, the compiler could be potentially able to use this and optimize the code in order to run better on that particular hardware. So this was just one very high level example of the kind of optimizations that can be applied. In order to really understand this more, it is a good idea to go a little bit deeper into how compilers work so that you can understand various kinds of optimizations. Now, so far we have been talking about parallelism, which basically in some sense is duplication. But before that, actually what we had was we had resource sharing, because the whole idea of a CPU in some sense is built around the notion of resource sharing. At the simplest level, the way to think about a CPU is there is one shared resource which is called the ALU, and we sort of build circuitry around that ALU in order to see how that single shared resource can be used in order to perform many different computations by time multiplexing them, right. Now, the benefit of a time multiplexed approach, right, is that you have less hardware, you have a single resource, right, as opposed to duplication or parallelism where clearly you are going to use more hardware, right. So, these are sort of in some ways two contrasting approaches that you would need to do whenever you are trying to optimize the structure of a digital design. Should you go for resource sharing, which would allow you to use less hardware but is most likely going to take longer to solve a problem, or can you benefit from having more hardware and thereby being able to perform computations in parallel? Now, the problem is just having more hardware doesn't necessarily solve the problem unless you have enough data that can actually make use of your parallel resources in the first place, right. So, there are a number of different decision factors that come in when you are trying to decide how you should go about designing your hardware. First of all, do you need extremely high throughput? If so, then duplication is probably called for at some point, right. Without that, you are not going to get extremely high throughput. Do you have a large amount of area available for your design? If not, then you probably need to do resource sharing, otherwise you are not going to fit into the available area that you have. What about power constraints, right? This can cut both ways interestingly, because you might find that you can actually run at a lower frequency if you have more hardware and therefore reduce power, or you might find that if you have less hardware, the total capacitance is less, but you need to run at a high clock frequency in order to achieve a given target. It could go either way. You need to sort of know more about the system in order to know whether power should guide you towards resource sharing or duplication. And of course, in case you have data dependencies, you might find that duplication is actually a waste of time. In other words, you cannot really benefit from having, let's say, 16 different multiplier units, because the data that you are trying to multiply actually depends on what was computed earlier. Right? So, there are a number of different decision factors that you need. In other words, you need to understand the problem you are trying to solve before you can take a decision on which of these optimizations to apply. The typical way that's done is you start off by implementing a simple logic, you then find out which components turn out to be critical. In other words, if you find that you are doing many multiplications and therefore your bottleneck is your multiplier, maybe you could just try and duplicate the multiplier alone, right. You might find in more advanced scenarios that your code itself is sort of dynamic and you need to sort of be able to change the amount of resources as and when the system requires it, right. Do you need more processors? Are we dealing with, let's say, a system with like multiple hardware units that can actually be pulled in at runtime, or is it something where your hardware is fixed and you only get to sort of choose a little bit about which instructions get executed at what points in time? The eventual sort of one interesting idea that is brought about, especially in the context of things like FPGAs, is you might even have the ability to reconfigure parts of your data path at runtime in order to say that if you have a large amount of computation of a certain kind that needs to be done, maybe you can add more resources of that type for a short duration, and once you are done with it, you can basically abandon it and go back to your original design. This turns out to be very nice in theory, very hard to implement in practice, but is definitely something, a possibility that is opened up by the use of FPGAs. So, overall, to sort of summarize this discussion on performance optimization, there are a few key techniques that we have talked about, right? Pipelining is probably one of the more important ones that you need to understand. It's primarily meant for throughput improvement. Parallelism applies whenever you have concurrent operation, meaning that if you have the ability to execute more than one operation at once because they do not have dependencies, then yes, you might benefit from actually having parallel hardware. Something that we did not talk much about was the memory hierarchy optimization, but we have looked at it in other contexts before, right? Especially when you have the slower memory versus faster memory, and where you should place your data in order to get the best computational throughput. All of this ultimately requires you to also have a good understanding of the actual algorithms or the problems that you are trying to solve, right? You should never get into the thing where you are purely focused only on digital design without understanding the big picture of what problems you are actually trying to solve. In terms of methodology, how do we actually go about doing these optimizations? The first thing is come up with a possible design and then profile it. Try and identify bottlenecks in that design. Then once you have certain kinds of ideas on where you might want to improve things, let's say that you have identified multiply and add as a very common operation, can you actually change your hardware? Are you allowed to change it based on the constraints on the system? And if so, does it make sense to try and add more multiplier units, right? Of course, verification of this entire system becomes crucial, right? You have to ensure correctness of your new design, and this entire process ends up being completely iterative. You need to repeat this until you are satisfied with the final results. All this of course doesn't come for free. This is ultimately an engineering problem, which means that this concept of trade-offs applies throughout everything that you are trying to do here, right? We already saw throughput and latency could be sort of opposing in nature, right? You might want to sacrifice a little bit latency in order to get better throughput. That after all is the key idea behind pipelining. You might be able to sort of sacrifice some amount of, or rather sacrifice some area, accept an increase in area but get better performance through using parallelism. Performance and power, the simplest way is to say that I can sacrifice some performance by operating at a lower frequency, which in turn would give me an improved power consumption, right? And ultimately it might even come down to what's sometimes called the time to market, right, which says how much time are you willing to spend on trying to optimize your system, right? Or do you just want to get something that is operational out as quickly as possible so that you can at least have it functioning and then maybe decide on whether it is worth optimizing further, right? Now with all of this in mind, there are a number of different future trends that you might be interested in sort of following up, right, in order to understand where the whole field is going. And at least as things stand right now, some of the big areas are domain specific architectures, especially in the area of AI and ML. Not just that, also in high speed communication, in various other kinds of signal processing applications. It turns out that having an architecture that is specific to the domain that you are trying to program for or build systems for can in general give you much better performance and much better efficiencies than using general purpose CPUs. Now the moment you have these kind of domain specific architectures, it turns out that trying to write code by hand for each of those things is humanly almost impossible. So how do we automate these processes? How do we get optimized code or optimized hardware that fits well for the kind of problems that we have, right? And not just that, we are also increasingly dealing with heterogeneous computing systems. There are CPUs, GPUs, neural processing units, image coders, audio codecs, all kinds of things on a single SoC, right? How do we make the optimum kind of use of all of these in a way that is able to balance out all the different functionality? All of these are actually active areas of research and would be interesting directions for those of you who are interested in going further into these areas.